morning, class, and welcome to our final recorded lecture in climate dynamics, climate variability, and climate monitoring. Today, we will complete our discussion on remote sensing and remote sounding instrumentation for climatology and meteorology by looking at a few examples of ground-based atmospheric remote sounding methods. So these are remote sounding of the atmosphere from weather stations that is stationed on the ground. First, we will look at an example of a passive remote sounding application from the ground, and such an example is Dobson ozone spectrophotometer. As the name suggests, this is for measuring the concentration of ozone in the stratosphere. It measures the column of ozone, that is, the number of ozone molecules in a column of atmosphere of unit cross-section. The typical units are kg per meter square. That is, if you have, say, a 1 meter cross 1 meter area, square area in the ground, and assume an imaginary column of air extending from the ground to the top of the atmosphere, that imaginary column of air will weigh something, and its value will be some kg of air per meter square of that column area. Of that, a part of it will be ozone. So, the kg of ozone on that column of air per meter square of the ground area is the weight of the column of ozone. In the UV spectrum, the solar radiation is only actively attenuated by the stratospheric ozone molecules and is not subjected to other types of atmospheric emission or scattering, which makes our measurements much easier. So, ozone will only be absorbed by the UV radiation will only be absorbed by the stratospheric ozone layer and will neither be scattered nor be reflected nor be absorbed by other parts of the atmospheric gases or dust particles, etc. Hence, in the UV spectrum, we can write the spectral radiation intensity at a certain UV radiation band frequency nu as detected at the ground level at an angle theta to be the spectral radiation intensity at the ground I nu 0 equal to the spectral radiation intensity at the top of the atmosphere I nu infinity of that of radiation of that frequency nu into the attenuation amount, which is exponential minus the optical depth of the atmosphere for that frequency tau nu at 0 into sec theta. Sec theta is 1 by cos theta. So we have derived this expression when we are looking at how shortwave radiation propagates through the atmosphere towards the ground. So this is the same expression that is being used here and is being exploited by Dobson ozone spectrophotometer. Tau nu 0 is the optical depth of the atmosphere for that frequency nu as measured from the ground level, and this is given by 0 to infinity the absorption coefficient for the absorbing species, which is ozone, for the frequency nu. So, K nu absorption O3 into the partial density of ozone in the atmosphere with respect to Z dz. Z is any height of the atmosphere from the ground. So, where the height is varying from 0 to infinity. So, this is the standard expression for optical depth. If we assume that the absorption coefficient of ozone is constant and does not change with altitude, which is a reasonable approximation to have, even though there is some temperature effect as we discussed previously, we can take the K nu absorption O3 as a constant and out of the integration. Then you get the partial density of ozone multiplied by the differential altitude integrated over the entire altitude. So, kg per meter cube into meter, which becomes kg per meter square. And this is what we are calling the weight of the column of ozone, MO3. So, here we are saying the weight of the column of ozone, and this is kg per meter square, MO3. And this is the value that we want to evaluate. So this is directly obtained from the optical depth value of the of ozone for that frequency nu. And we have assumed that the spectral absorption coefficient is independent of altitude, as we have seen. So now we just put this expression in place of the optical depth expression in 10.13. So T tau nu 0 we are replacing by the absorption coefficient into the weight of the column of ozone. So we get expression 10.15, I nu 0 equals to I nu infinity exponential minus k nu absorption ozone into MO3 into sec theta. Now this is what the spectrophotometer, this I nu 0 is what the spectrophotometer will observe the radiation intensity to be at a frequency nu in the UV spectrum when it looks at a certain angle theta with respect to the ground normal. However, we can measure the same thing at a certain different frequency nu prime which remains in the same UV spectrum band. So UV spectrum is has a certain bandwidth, right? So we take two such frequencies, nu and nu prime, and ask the spectrophotometer to measure radiation frequency, radiation intensity for both these frequency bands. So at nu prime, the expression will be I nu prime 0, what the spectrophotometer measures, equals to I nu prime infinity, what the actual radiation frequency is at the top of the atmosphere for this frequency nu prime, into again the same expression, only the absorption coefficient is changing because the absorption coefficient is dependent on the spectrum. This is the spectral absorption coefficient. So K nu prime absorption ozone. So this is the absorption coefficient of ozone at the frequency nu prime, while this expression here 10.15 is the absorption coefficient of ozone at a different, slightly different frequency nu, both of which are in the UV band. So we get equation 1015 and 1016. Now we divide these two equations and take logarithms. So natural log of I nu 0 by I nu prime 0 equal to natural log of I nu infinity by I nu prime infinity, and when you take log of exponential, this just becomes this expression here. So this then becomes a multiplication, right? So this becomes K nu prime absorption ozone minus K nu absorption ozone into MO3 sec theta. Because this is minus, this minus comes through division, this becomes positive. So this becomes K nu prime absorption ozone MO3 sec theta. Okay. So we first take the division and then take the log. This log becomes a ratio, this log becomes a ratio. Log of exponential becomes a simple summation. So you get K nu prime absorption O3 minus K nu absorption O3 MO3 sec theta. So this is equation 10.17. So why we are doing this? Suppose we take a variable y, which is the ratio of these two frequencies, radiation intensity values. We call this variable y, log of I nu 0 by I nu prime 0. We call x variable as sec theta, that is 1 by cos theta, we call variable x. And we call I nu infinity by I nu prime infinity log of that as a coefficient a, and K nu prime absorption minus K nu absorption as coefficient b, this into MO3 as coefficient b. Then if you see this expression, this becomes an expression of a straight line, y equals to a plus b into x. Okay, so this entire 10.17 can be recast as an equation for a straight line with variable y as this ratio, log of ratios of the observed spectral radiation intensities. Variable x is the zenith angle sec theta. Coefficient a is the log of the ratio of the actual spectral radiation intensity to the top of the atmosphere, and the slope m of this slope b of the straight line is the difference between the mass absorption coefficients for these two frequencies into the weight of the column of ozone. Now, what we can do, why we can measure directly. A, we can get from the solar blackbody radiation intensity spectrum. Okay. So, Y is evaluated, A is known, X we can measure because we know the orientation of the spectrophotometer. So, the only unknown is B, correct? And what we can do in this context is that we can measure for multiple values of zenith angle theta. So, we can change the inclinations theta, theta 1, theta 2, theta 3, theta 4, etc. and get y1, y2, y3, y4 and plot a linear line of y versus x, correct? So, this is just a linear plot. For every zenith angle theta, we will measure y separately since A is known and x is y separately and we know the x, the zenith angle basically. So, we can plot the straight line on a plot. The slope of this line then we can get graphically and the slope of this line is just b, correct? So, from the measured data, we plot a line, we get the slope of this line and the slope of this line is the difference in the mass absorption coefficients into the column of ozone weight. From this, we can get the mass absorption coefficient as the slope divided by the difference between the mass absorption coefficient of the ozone. So, the column of ozone is equal to the slope of this empirically obtained straight line divided by the difference in the mass absorption coefficient of ozone. And the mass absorption coefficient of ozone for these two frequencies can be measured separately and we can evaluate them. Hence, we can get the value of the column of ozone. So, this is a very convenient way to continuously measure ozone concentration in a certain location using Dobson spectrophotometer. Next, we look at an active atmospheric sounding technique, which is radar based atmospheric sounding. Okay. So, radars can be used for active ground based remote sounding. There are multiple applications of radar. They can also be used from satellites, from planes, from reconnaissance aircrafts, everywhere radar is used. Here we will look at remote sounding principles for radar. Here microwaves or radio waves are emitted by the station and the backscatter of these waves. So, this is very important and this is a kind of a different concept here. We are looking at the backscatter of these waves back towards the receiver of this station and important atmospheric properties are evaluated based on the backscatter of these microwaves and radio waves from features in the atmosphere. So, we are not looking at the transmission or absorption of various of the radiation, but the scattering or reflection of this radiation from various atmospheric features. So, the weather radars utilize backscattering of microwaves from water drops and ice crystals in the troposphere to estimate precipitation rates, thus providing important data for weather forecasting systems. So, weather radars primarily work in the microwave zone and they emit microwaves and these microwaves get scattered back by water drops or ice crystals in the troposphere and hence radars are used to measure weather fronts, precipitation rates, etc. A different application of radar that we will discuss more here in this discussion is using radio waves, which are reasonably large wavelengths, a meter or so, which are emitted by weather radar stations to find features in the lower and the middle atmosphere. Since these radio waves get scattered due to inhomogeneities in the refractive index N of the atmosphere. So, unlike microwaves, which get scattered by basically particles, raindrops and ice particles, radio waves get scattered due to changes in the refractive index of the atmospheric gases themselves. So, refractive index changes are caused primarily through changes in density, due to changes in the velocity, changes in pressure, rapid changes in pressure, or ionization of the atmosphere. Okay, so these cause inhomogeneities in the density gradients primarily, and these cause change in refractive index, and the change in refractive index causes the scattering effect. So the variation in refractive index may arise due to variation in temperature and humidity. So again, so temperature and humidity variations cause density variations, and density variation cause refractive index variations caused by patches of atmospheric turbulence due to stratification of atmospheric properties in thin layers or due to regions of ionization. So the most common reasons why refractive index changes is due to variations in temperature and humidity caused by patches of atmospheric turbulence. This may be large, fast-moving wind fronts, rapidly fluctuating values of pressure, temperature, etc. So these are called turbulence. Okay, due to stratification of atmospheric properties in thin layers or due to regions of ionization. So, for example, meteor or comet trails or regions of lightning, these cause ionization of the atmosphere, and these also cause variations in refractive index. So in radars, an important feature is differential scattering cross section, d sigma d omega. So while it's called d sigma d omega, it's actually not a differential. The symbol itself is d sigma d omega, okay, which is defined as the scattering power P at a certain along a certain unit vector n. So that is why it's called Pn. So basically it's called watts because it's called power because it's watts per unit solid angle by an object in the direction n divided by the incident flux F. So suppose you have a particle or an inhomogeneity in the atmosphere. There is an incident flux of radiation F coming to this particle or inhomogeneity, and a part of it is being scattered back. The amount that is scattered back in the direction n over an unit solid angle omega is the differential scattering cross section. So d sigma d omega is the scattering power Pn divided by the incident flux F. Okay. So per unit incident flux, what is the power that is being scattered back in a direction given by the unit vector n over a unit solid angle omega over that direction? This is called the differential scattering cross section. And it can be shown that the differential scattering cross section is proportional to the square of the frequency of the incident radiation that is coming and getting scattered. Okay. So if the incident radiation is at higher frequency, greater is the scattering that is happening per unit incident flux. Okay, and that ratio is to the power 4. So frequency to the power 4. Okay. So we will use this expression now and derive certain relations for radar scattering. Consider a radar that is emitting pulses of power Pt within a cone having solid angle alpha. So we have a radar which is emitting pulses of radiation with a certain power in wattage along a cone whose solid angle is alpha. Okay. First, we will look at a isotropic scatterer, so like a particle kind of a thing. Okay. So we have a surface which is scattering. So isotropic scattering means direction independent scattering caused by a certain surface. It may be a strong inhomogeneity or a particle, etc. Okay. Or say a cloud, for example. So the bottom of the cloud can act as an isotropic surface, for example. We have a single isotropic scatterer with a scattering cross section d sigma d omega at a distance r along the cone axis. So we have, say, the emitter is emitting along a cone. This is the cone axis, and this is the angle alpha, solid angle alpha of this cone, along which the power Pt is being emitted. and we have an isotropic scatterer at a distance r along the cone. So if this is the station and the surface is located here, the distance between the surface and the emitting station is the distance r along the cone axis. Then the energy flux incident on the scatterer is Pt by alpha r square. Alpha is the solid angle, r is the distance between the emitter and the isotropic scatterer along the cone axis. So alpha into r square, alpha is the solid angle, we will get the total energy flux. So this F is basically Pt by alpha r square. Okay. If the radar receiver has an antenna area A perpendicular to the cone axis, so the radar not only transmits the radiation, it will also have a receiving antenna. Okay, and this antenna will have a certain receiving area A. So if the receiving area is A perpendicular to the axis of the cone, because it will scatter back towards the transmitter along the cone axis only. Okay, then it subtends a solid angle A by r square at the scatter. So the radar has a area A, radar receiver has an area A projected to along the cone axis. So this area A is subtending a solid angle A by r square itself on the scattering surface. Thus, the backscattered power received by the radar will be Pt by alpha r square, which is the flux, into A into d sigma d omega. Okay. Remember, d sigma d omega is Pn by F, right? So the F cancels out basically, and you have A into Pn. Okay. So the total expression then we will get is the received radiation is whatever is the scattering cross section d sigma d omega into the area A of the antenna projected along the cone by r square. So this solid angle A by r square, and then the incident flux Pt by alpha r square. Alright. So this expression gives us the total radiation in terms of wattage that is received back by the antenna. So this is the expression when you have a single surface that is scattering back the incident radiation, okay, like a cloud, bottom of a cloud surface. However, in many cases, scattering happens over an entire volume. Suppose the bean cone contains n scatterers per unit volume, each with the same differential cross section d sigma d omega. Alright, so we have, instead of a single surface, we have a large volume over which the scattering is happening and which contains n number of scatterers per unit volume. So it may be containing a lot of particles, for example, and these particles are scattering, and this particle number density basically is over a certain region of the atmosphere is n. Okay. Each of these particles, we assume, has the same scattering cross section d sigma d omega, and these are arranged in a volume between the distances r and r plus delta r across the cone axis. Then if the beam cone axis is inclined at an angle theta with respect to the ground normal, so if the ground normal is this, the cone is angled at an angle theta, and we have a certain volume between r and r plus dr where the scatterers are located, then we can show that the received power is again the transmitted power into A by r square into cos theta. So this cos theta term comes, and this alpha by r square is removed. Okay, so this is transmitted power into A by r square into cos theta. So the cos theta term comes into delta r, the distance along which the scattering particles are located, into two coefficients, beta and eta. Beta is the volume scattering coefficient, and this has to be empirically determined how the scattering happens per unit volume, and eta is the efficiency and geometric factor for the radar. So the radar efficiency itself and radar's geometric factor is given by eta. Okay. Here the volume scattering coefficient will depend on the refractive index changes of the scattering volume. So if over a certain volume, due to inhomogeneities of the atmosphere, refractive index changes, then the volume scattering coefficient itself will be proportional to the refractive index gradients, okay, and has to be determined separately from physics concepts. Okay. So knowing the received radiation, the transmitted radiation and other factors, we can evaluate beta. From beta, we estimate the refractive index changes in the scattering volume, and this information is used to estimate the properties of the scattering medium. Okay. So we know PT, we evaluate PR, we know A R square cos theta, the radar efficiency is known, the delta R is known, so we get the beta value. So from our data, we actually evaluate the actual value of beta, and then there will be a correlation from physics principles between beta and the refractive index gradients, and using that we get the properties of the atmosphere we want. Okay. One of the important applications of radar is evaluating atmospheric wind speeds. Okay. So let us assume that the scattering is happening due to a turbulent patch in the atmosphere that is moving along with the wind with a velocity u. If the radar is pointed at the direction given by the normal vector n, so suppose the radar is pointed at a direction given by the normal vector n, then the velocity component along the radar direction is n dot u. So u is the velocity of the wind which is moving this turbulent patch, which is reflecting our radiation. Okay. And the radar is directed at a normal vector n. So the velocity component that the radar will see is along this normal vector n. So it is n dot the u, the velocity vector u. Suppose we emit two short radar pulses at t equal to 0 and t equal to t0. So we are emitting two successive radar pulses, once at 0 seconds and one say at 1 second. So t0 is 1 second, for example. So we are periodically emitting the radar after say t0 second intervals. Okay. It can be shown that the time difference between the receival of the reflected waves will be given by, so because the turbulent patch is moving with the winds along this by v dot u, the reflection time between the pulse that is emitted at 0 seconds and the pulse that is emitted at t0 seconds will be changing, because the turbulence patch is either moving towards or moving away from the data at a velocity v equals to n dot u. So the time between the receival of this reflected pulses emitted at 0 and t0 is given by t0 into 1 plus 2v by c. C is the velocity of light. Okay. So if v is positive, the turbulent patch is moving further away, so that distance, the time between the pulse receival will be greater than t0. If v is negative, the patch is moving towards the radar, so it will be 1 minus 2v by c, because v will be a negative value. Okay. So this is the total expression of the time between the received pulses. Okay. Now the initial angular frequency of the emitted wave is omega 0 equals to 2 pi by t0. Because the time interval is t0, the angular frequency of the radiation pulses is 2 pi by t0 that was emitted. But the reflected pulse will have a different frequency because the time interval is changing. So the angular frequency of the reflected wave, omega r, is omega 0 divided by 1 plus 2v by c. Okay. Since v by c is very small, it's a small value, we can do a binomial expansion and we say this is almost equals to omega 0 into 1 minus 2v by c. Because speed of light is very large, right? So this velocity will be much smaller than c. So we can easily write it as the initial angular frequency of the transmitted radiation into 1 minus 2v by c, where the v is the relative velocity of the patch with respect to the radar. Okay. Based on this expression, the wind velocity component can be determined. So in this context, we do not have to evaluate refractive index or anything. This is just looking at the frequency of the transmitted, the reflected radiation. Based on that only, we can get the velocity component of wind. And by changing the radar direction, we can shift the radar transmission direction from one zenith angle to another zenith angle, and we can get all the components of the atmospheric wind velocity through remote sensing alone. So this is a very effective method of measuring wind velocity from remote sounding methods. Okay. The last remote sounding ground based system we will see is Lidar, light detection and ranging. This is also an active atmospheric sounding technique where we are doing vertically directed. So here the direction is normal to the ground always. Vertically directed laser that transmit pulses of radiation in the UV and the visible light. So laser is a single frequency, almost a single frequency synchronized radiation, and the frequency is in the UV and the visible range. So the difference between radar and Lidar is radar works in microwaves and radio waves. Lidar works in the UV and the visible range. Okay. The backscattered radiation is measured after a time delay at the transmitter side. The principles are similar to that of a radar, but unlike radio-based radars, the effects of atmospheric attenuation must now be considered. Because it's the UV and the visible range, there will be some amount of atmospheric attenuation, absorption by the atmospheric gases itself. And the scattering takes place by molecules and aerosols rather than refractive index variation. So Lidar is used to measure gas composition, atmospheric density, aerosol concentration, etc. Okay. The received power PR is equal to transmitted power into exponential minus 2xz. X is the optical path of the radiation frequency up to the height z. Okay. So z is where the scattering is taking place. So the optical path of the frequency up to z is xz. It's 2 times this because it is going up and then coming back. So it's twice z, right? So it's 2 times the optical depth exponential. So this is the attenuation part. Nz is the number density of the scattering species. Whichever scattering molecule is doing the scattering, the number density, say moles per meter cube, for example, that is the scattering species. Eta is the optical efficiency of the receiver. D sigma d omega is again the scattering cross section, and A by z square is the same as A by r square. Here we are talking z only because the Lidar is always vertically directed. So it's the altitude z of the scattering section. So A by z square. Okay. So this is the total received power, and we are interested in the number density Nz value. Alright. So the height z is inferred from the time delay delta t equal to 2z by c. So just looking at the time delay between the transmission and receival of the frequency of the radiation, we can find the time delay between transmission and reception of the pulse. If the pulse length is tau, so every pulse will have a certain duration over which the pulse is being emitted, then the range resolution, that is the error, because the pulse has a certain finite length, the time, it's not a sharp difference between the emission and the receive. There will be a small time interval. So this will cause a range of z that will be obtained. So this range resolution delta z is c tau by 2. Tau is the pulse duration. Okay. So Lidar can only resolve up to delta z the spatial properties. Okay. Because the tau is quite short, the range resolution usually varies from few tens to a few hundreds of meters. Okay. So the reflection range resolution delta z is between 10 and 100 meters approximately. So now from equation 10.22 we can obtain the number density Nz of the scattering species at height z, since everything else can either be measured like PR, optical density, etc., or obtained from physical principles and correlations. Okay. We also note that d sigma d omega as before is a mu to the power 4, where a is a species dependent constant that is separately evaluated. Okay. So from number density, the partial density of the scattering species can be determined, because partial density is molecular weight of the scattering species into number density. So if this is number density is moles per meter cube, then this is how we write it. Atmospheric density measurements can be done by Lidars emitting at wavelengths less than 3 micrometers. Okay. So if you emit wavelengths less than 3 micrometers, the atmospheric density measurements can be done by Lidars with wavelengths less than 3 micrometers. Lidars with tunable dye lasers are used to emit very specific frequencies that are scattered by trace species in the atmosphere. So if you want to measure certain species which is scattering strongly at a certain very well-known frequency value, then you can use a tunable dye laser to emit that specific frequency and get the trace species concentration at a certain altitude Z as well. So that is also a very common use of lidars. So atmospheric density trace species measurements are done by lidars as well as aerosol measurements. Okay. So with that, we close our discussion on remote sounding and remote sensing principle, and this finishes the main lectures for the class. Hope you enjoyed our class, and best of luck for the exams and your assignments. Thank you for listening, and have a good day.